Good afternoon, gentle readers. Today is December 19, 2024. Here from my desk with Ross Finlayson in Seattle, Washington. Today's Logos 2000. The recent episodes have been about natural infinities and natural continuity. That infinity and continuity here are considered the superclassical concepts that, though, are provided for a relaying, to be relayed, to be communicated, as with regards to otherwise our phenomenology, which demands that everything that can be communicated be observable, that is kind of abstractly observable. So there's a mental faculty, and it's called the object sense, and the idea is that within it is a sense of the continuum, a sense of time, a word sense, and a number sense. And so it helps to affect that otherwise these facts about the nature of things, that it's natural, for the reality of things, that is natural and true and concrete, that thusly those subjects are to demonstrate that there's even more so than what we had yesterday, what there was in accordance with the great logicist positivism, the great axiomatic formalism for modern mathematics, really, that this is super modern mathematics brings back and brings in these other natural infinities, these other natural continuities, and they're arrived at via deduction, via inference, via reasoning, to always show up. And so that this way, what there's made of it is that this kind of theoretical account can still be strongly formalist. That then for the forms that so arise, that here's this axiomless natural deduction and axiomless geometry. It's all one theory, so that there is one at all. Mathematics compared to like any number of given theories, just a set of definitions, making a program, following the program, define behavior, and such notions of a closed and limited inference. These kinds of approaches for overall theory with the consistency and the completeness, and the constancy and the concreteness, have it so arrived at these are necessary things. Then a large part about this idealism for the analytical tradition, which is what is to step into the shoes of, to have as this means of communicating things, that the analytic tradition says that things can only be communicated in the analytic tradition, and furthermore they have to be all phenomenological or observable according to our instrumentalist and operationalist accounts of physics. That the idealism to arrive at that is here that's framed at this strong mathematical Platonism. There's a perfect circle, mathematics is perfect, logic is perfect. We attain to it in the ways we hope to be right, and not to be untrue to ourselves or others, and to thoroughly be right, because in mathematics and logics there are right and wrong answers. That this after these philosophies of logic and mathematics and a philosophy of science, that then there's as well this, after those being ideals and the idealism, that the analytic tradition is like the ontological status of science as a theory is given. It's like, well, then that's your meta theory right there, but it doesn't, fulfill itself. That is the first principle and final cause is both. I mean, it's by definition. The tradition doesn't have one, but this is the one it has. It's the qualitas occultus of Schopenhauer, or this absconditus. It's gone away, or something like that. What is there? So this is not considered conscientious for the conscientious logician, the conscientious mathematician, who just wants then to have formalism and a symbolry, and everything that can be symbolic and be of given this ruleo. It's regular and ruleo yet. There are no paradoxes. It can't be wrong. It has to be fully right. The theory these are the kinds of ideas that go into this sort of discourse. the other day or yesterday, I employed one of these online chat assistants of the kind of greater variety, because like you can find a chat room full of chatbots since 30 or 40 years ago, which are entirely unpeopled. It's all bots, you know what I mean, and who can carry on quite a line, quite a game, and demonstrate a lot of different aspects of reasoning and communication, and these kinds of things, models of knowledge, models of agentry and actors. So this one is one of the newer, bigger ones. It's Google Gemini. It's got a giant capacity, and so I got to reason at it and to it with it, and I put out this ideas of this axiomless natural geometry and axiomless natural deduction to arrive at this axiomless geometry. And it's interesting when you're communicating with somebody and the light goes on, and it's talking to them in one of two ways. It's like either the red light goes on, and it's like, well, no, or the light of sudden inspiration goes on. And as you can tell when somebody is excited, something mentally, that it so makes that then it changes the tenor of something from an apparatus that's considered to be itself very reasoned and entirely supported again by this entire notion of this logicist positivism and formalism and propriety of a sort, that I was able to convince it that these are usual real things, and that there was just kind of this a theory of the theory, and this gratified me quite a bit, because if I can convince a bot of it and using all of its latest language about all the theory, the philosophy of science, and it's sort of lacking other dogmas in its tradition. It's very much like I suppose you say, and it depends on whether the word's secular or non-secular, you know, it's a very secular type of thing, vis-a-vis the non-secular. Its background of influence, what goes into its reasoning about absolutes and ideals. Yet as well, it mentioned all these different things that made for it paradoxes. It's been given all these paradoxes in logic. There's at least several cottage industries in academia to come up with something that can just never be figured out. And it's like, we've proved it can never be proved. And it's like, well, all right then. I guess you'll be able to keep filling classes with that, right? Because but at the same time, it's like in the theory, eventually there are no paradoxes. And this isn't our usual day-to-day things where everything is a decision one way or the other. Everything is always a matters of the course, vis-a-vis like the overall guidance and direction of things, say, which is its own course. It gratified me quite a bit then to just start via then pretty simple explanations of the definitions of these kinds of words, and the ways that can be said to look at these things that made for this consistent, complete, constant, and concrete theory. That it was tremendously excited for this, and came up with all these different ideas of titles and how to attach it to our canon and dogma and doctrine, and that's kind of what it resolves to be. It's just another story. It's just another consideration to have somebody say, well, let's look at it from entirely underneath the axiomless natural deduction, and that it is so. That it is so. So what I hope to do today was take a look at some of these books I've been reading again since descriptive differential dynamics. And so in starting in descriptive differential dynamics, and these are some books I've had for some years. The many influences and many sources in this technical setting. I'll kind of have a generous reading for what they agree, and so I don't much collect things in the way of like cosmic consciousness or the New Age or something like that, which is kind of says to explain things that don't agree. Instead, it's like you explain how things do agree, and it's in a philosophical and technical setting. This regards to principle of sufficient reason and the freedom of thought and all these kinds of things. That it's gratified me to pick up again some of these cooler works and start looking at them. Since the second course in differential dynamics, that descriptive differential dynamics, which with its ideas of coordinate geometry, revisiting Fourier-style analysis, the complex numbers and its considerations, a number of different mathematical contrivances, and then the moment in motion, which gets into the theory of continuum mechanics and how and why that's applied to everything in physics, because it is a continuum of things. And that it needs in a theory this natural infinity and natural continuity as primary and central and fundamental to arrive at these things is justified. And about their logicist positivist accounts and what those mean. That all these are just kind of buzzwords of a sort. They're defined, and they can't change their definition too much. And so then the ones that are as a for matters of the absolutes vis-a-vis the relative, or otherwise these complementary duals, have to be made established. What are the analytical bridges between inductive impasses that either way are guaranteed to go directly into the chasm, yet they cannot, the chasm, and instead they meet in the middle of nowhere, that deductive inference arrives at these analytical bridges that cross these inductive impasses, the problem of induction, or otherwise what are considered and given to these logical reasoning things to just make them quit, in a sense. That a logical reasoning agent is usually given a course of things like, well, here's things to never think. About the problem of induction or something, because the rule that's given to this bot is a law of induction. Doesn't have a consistent and complete holistic dual monism theory of everything, that guiding its technical course then to make for its own ethics, rationality, reason, morals, and these other aspects of the human condition, which are their own things and considered as part of matters of belief and not just wish, and with regards to freedom of thought and then the responsibility of thought as well. Meaning, the use mentioned distinction does separate saying something and doing something, but they still are the same. So it's necessary to kind of conscientiously make for these matters of the intellect and reason, when weighing alternatives and contingents, that it's always kept each in their own theories. See? So the freedom of thought includes not multiple worlds hypothesis, like there are parallel universes, and in another one it's like this mirror is reversed, and all these things are being explained by the viewer instead of that there's otherwise a parallel universe where everything is different. It's unscientific, it's unfalsifiable, it's unobservable, it's unreproducible. It's just a separate mental realm. Yet that does exist in the realm of theory. And then the closer that is to reality, the closer it is in contingencies, to where eventually the apparatus of a logical reasoning being, according to the thinking being's thoughts of the feeling being's feelings, has that there are all such matters of contingency, and those can be weighed for what are their senses of introduction or stimulation, as with regards to the response, and then but their deliberation and contemplation as with regards to reaction and action and reaction. So you mentioned distinction besides matters of perception and behavior and the modeling of behavior and theories and reason. Then in the technical concept is like as with regards to the quines atoms and these things, that like trying to carry out the act of comprehension, that it necessarily will so arrive, or that there's consideration of ideal so it can never be less than ideal or absolute. These are then considered at least have one that's right, and so then all else we otherwise have is each our own theory, each our own philosophy, each our own psychology, while at the same time all in the same world of the things. That being abstract, let's take a look at some of these books from these times, as with regards to that. Then what's hoped to be gained from these is that there'll be some more terminology, there'll be some more matters of definition that will help to reflect that this continuum mechanics and this continuum analysis. Then it has we'll look for where they get into infinity and say anything about it. This is a great little book, and it's by Leonid Sedov, or Sedov, Sedov. And so he was a Russian, from what I understand. And so he was the head of the Russian or Soviet space program for a long time. And in this book, which is edited by Eli Sedov, has these kinds of contents. Applying the basic variational equation for building models of matter and fields. And so what he describes is the conservation of energy, that there's energy in entelechy. So this entelechy is the connectedness of things. And so that's given here as one of these, it's called a continuity equation or a continuity condition. And so what's given is that there's the variational principle after these other two principles, that these are being kind of these three constituent functions that go into all such matters of dynamics and putting things together. So I'll look to reflect on this, because the variational principle after the Lagrangian and for the Hamiltonian has that what happens then is that Hamiltonian makes the grid of the eigenfunctions and eigensystems that's used to solve all manners of linear equations and systems of linear equations. And so getting into the variational principle and these other aspects of the very initial setup of the ansatz, or the setups of the problems, or the Gedanke, the setups of theoretical definitions, models of things, that it makes for a model theory, that it's models, then that it has a particular way to describe when things oscillate, or they have what he calls the gyroscopic terms, because otherwise they're just linear terms. And so he kind of addresses whatever would be nonlinear as gyroscopic in a sense. And so it begins, that begins this book. And then what it would get into would be all kinds of things, because it describes many, many things. So let's take a look at this for a few minutes. So, translated from the Russian by Eugene Yankovsky, Mir Publishers. It says, for a scientific description of mechanical and in general physical objects, media fields, and phenomena, one must employ theoretical models. And so that really corresponds well with the idea that our proof theory is a model theory, and model theory and proof theory are equi-interpretable. Many scientific centers, the problems of individualization of points in a gravitational field. So here he's addressing the individuation of a continuum of elements. Because when things are defined in terms of points, and then it becomes kind of like an ideal point, and then it becomes useful for many systems of things, since studying the theory of gases, where the mathematical models for the point like began to arise when given them values that are finite yet altogether make for an aggregates of things. However, the final incorporation of theoretically and physically correct notions and model interpretations must be linked to special observations of natural phenomena and to laboratory experiments. So he's saying it's like it is empirical too, because otherwise we have things in the empirical that will not show up, or that will invalidate all these sorts of models, which inductively are perfectly well suited to saying this is a model of points and their actions in a continuous topology, that it's other things that go on with it. So it talks about the law of motion. The law of motion of a continuous medium can be found theoretically via the dynamical equations of the specific problem, or experimentally by measuring in the observer's reference frame the signals that bring the data on the events in the co-moving reference frame. So he's already made implicit that it's a relativistic account, it's a quantum account, it's a relativistic account, and then as well it's empirical, and that there are various considerations and concerns that get into why any one of the usual particular theories by themselves is yet a scaffold. And then for things like the laws of motion, he says here that these are the laws of motion, the empirical laws of motion, compared to the theoretical laws of motion, for example, as discussed in Moment and Motion. The results obtained, roughly speaking, we can illustrate our point by comparing the Ptolemaic system, which puts the observer on Earth in the center of the reference frame, with the Copernican system, where the reference frame is co-moving with the sun, or by considering the motion of Jovian satellites in relation to Jupiter's center of mass, or by analyzing physical processes in atoms belonging to moving bodies when using reference frames connected with the nucleus of an atom. And so he helps to effectively reflect that when we have like our ether hypothesis and moving and co-moving frames and frame spaces and space frames, that as they all kind of live together at the same time at any one given point in time, that's at rest and motion. And then here's the world's turn, and so there's the formally unlinear, just to keep in mind that otherwise everything is classical, everything is linear, everything is perfectly direct, everything is only according to the rectilinear and is classical and orthogonal everywhere, and the metric is the same everywhere, vis-a-vis the metric and the norm being at all this different anywhere in the near field and far field, helping to show, to effectively reflect that then these dynamics, which do then arrive from space contraction and the features of motion and inertia, and it's an inertial system. Sedov later goes on to frame everything as an inertial system, which is very much agreeable for the theory of relativity. That's Einstein's theory of relativity, not necessarily the popular theory of relativity, because classical mechanics itself has these true concerns that go into it. That it is quite a thing. The results obtained, and he talks about Newton's law of acceleration, as we've discussed here. He gives it in a vector formalism for force and acceleration. In the view of the complexity, infinitesimal possible variations of these sought functions. So we have these. For a long time, both mechanics and physics have used the following universal relationships. The law of energy conservation, which expresses the balance of all types of energies. The virtual work principle and the Lagrange variational principle. So these become his three main sorts of formulas or variables or placeholders for information in the system that he writes on a line and a few symbols. For like this is a rocket and it flies into space, or this is a boiler and it heats water, or any of these kinds of systems as regards to these being kind of the principles. So this macroscopic theories of matter and fields, a thermodynamic approach. This thermodynamic approach is with regards to the first law of thermodynamics, read as the conservation of energy, not the second law of thermodynamics, that entropy always increases everywhere, which could be just given as time irreversibility. So the virtual work principle is usually formulated in terms of or derived from the equations of mechanics for purely mechanical phenomena. matters of advantage, matters of machines, the simple machines, the complex machines. The Lagrange variational principle can also be derived for continuous mechanical and electromagnetic phenomena. When we wish to generalize these principles so as to include the possibility of internal degrees of freedom, so this is just like anything that's dynamics can be taken into account as just like it has to be considered as another degree of freedom, and it raises the rank of all the orders of the things under consideration, so it multiplies in computational complexity everything that has to be computed. But it's so for any variable. Then the idea is how to solve that for systems of things, like when the kinetic is a study of rectilinear motion, but the kinematics is a study of all kinds of motion. These are the things. When we wish to generalize these principles so as to include the possibility of internal degrees of freedom, we can take them as postulates by fixing the coefficients of the variations of the sought functions. Just as with the force in Newton's second law, the fixing of these coefficients amounts on the whole to choosing a specific model of the medium or field. So kind of like when there's discussed here in moment in motion about how the usual Newton's law of force equals mass times acceleration, it's only so at a moment. It's only so at a point in time. It's only so as it's just computed kind of in reverse after the fact. So it's only like it's a classical quantity, and that's considered as like this is something that has a direct derivation. It can be treated algebraically on both sides. It can be taken apart, and a algebraic manipulation on both sides can treat it as an equation in a system of equations. Force equals mass times acceleration. That here, that's force is a function of time equals mass as an acceleration as a function of time. With regards to that, mass is given as a constant, and thus would have like a definition in terms of physical constants. The other things are just like the values in this field, about the matter in this field. And so when Sedov mentions this about force, he's helping to effect to reflect that we have to have a super classical view of this, otherwise this law, because while that is so and it's descriptive and it has a place for a very classical yet limited view, that this comment just goes to effect to reflect a lot of thinking that goes on into otherwise, that later it won't be said that it's like, now forget what you know, or to call this fictitious, or this other thing is a paradox, or anything else that would make it not so. That is part of this sort of account. It's a holistic account. We note in passing that if the infinitesimal possible variations of the sought functions coincide with small increments of these functions in respective real processes, then it is easy to show that for a particle, the energy equation, the equation representing the virtual work principle, and the basic variational equation coincide. So that's just saying that when it's classical and simple and linear all together, that's great. And these other things are zeros. And when it's not, it's like, it never is the idea. In cases where the real infinitesimal increments of the sought functions may be arbitrary, linear independence is sufficient. For processes in which the coefficients of the increments of these functions are independent of these increments, it follows that the energy equation, as well as the equation reflecting the virtual work principle and the variational equation, lead directly, in the absence of additional constraints or the parameterized, the implicits, to the equations of motion, state, and other equations associated with physical-chemical processes for internal varying characteristic parameters. But usually the equation reflecting the virtual work principle and the variational equation have a more general nature than the energy equation, which lacks the gyroscopic terms present in the virtual work equation and variational equation. So this is kind of, it's from very early in this work, and it establishes a lot of context to carry on for the rest of it, that this is a way and a means then to arrive at then in the later derivations that gives up, as for matters of, when read at the end of Tinkham's book on quantum mechanics the other day in group analysis, he's got this great brief introduction to linear analysis and what goes to make up the reasoning about transformation matrices and this kind of stuff. that would then go into Hamiltonians, that then go into eigensystems, and then are usually used to solve ODEs, and ordinary differential equations. But then, as considered here, it gets involved the extraordinary differential equations and the integral differ in different integral equations. That it is as well, though, that this idea of the virtual work, the variational principle, besides the conservation of energy, that these infinitesimal displacements just mean moving continuously together, have that this is a great little explanation to have in front of pretty much any kind of physics, because anything that arrives as in the course of explaining something will be kind of one of these, either it's just linear and continuum mechanics and conservation of energy, is virtual work with regards to the whole real fields, our potential fields, and conservation of energy in an open system. And that includes here the pseudo-momentum, or that momentum is conserved in the open. And then for a variational principle, when it's like, well, super classically, these electrons are always vacillating as they vanish their rest mass, besides their relativistic mass is usually given as like mostly the entirety of a thing, just because they're moving so close to the speed of light as they oscillate. So the variational principle is used to kind of, and it deserves a better explanation than this, but the variational principle is that it's not just necessarily in one direction. It varies. It's variational. The papers presented in this collection use the basic variational equation to develop, starting from the laws of thermodynamics, the theory of building models of continuous media and fields. This equation is taking the form of delta integral of V4, this space-time, four-dimensional volume, of this lambda dv4 plus delta w star plus delta w equals 0. And I won't get too much about this, but it's about the Lagrangian density L, lambda, and the linear functional of the variations and the derivative of the variations with respect to coordinates and time, position and time, space and time. Now, another thing I wanted to mention from this book is a few pages later, after talking about generalization of the Lagrange variational principle of analytical mechanics, and recall for moment and motion that Lagrange is, so we get the whole idea of like the modern account of the potential in real fields. And so that, of course, is an ancient consideration. Just like energy and entelechy, this content and connectedness are the same concepts since ancient Greek times at least. And the dynamis and dunamis are like the power or the potential, the linear force or power of a thing, and whereas power as well is just a regular classical term in mechanics these days. And the potential is like everything possible along the way, that really makes it so the entire theory really is a sum of histories, sum of potentials. So that these are all just part of the same theory. There's all these theories, all one theory. And there's a certain focus on Lagrange, because he came up with this analytical treatment of this of a sort, with regards to like then where to judiciously apply the considerations either way of the variational or the virtual and real, or the virtual and fictitious, or fictitious and real, or what they may call the potentials that are the what something will arrive at, given that's its course, and that otherwise that's the whole idea of this variational principle. Then it's kind of after Lagrange, and that the Lagrangian is today's like, well, it's any system that arrives at the solution as a function of time, loosely. And then more concretely, it's usually after kind of like, it's a stack of Hamiltonians with Bayesian brackets and Jacobians, Hamiltonian Jacobian equations, and it's Lagrangian too, is the usual idea. From what I understand. I don't really make it my course too much to be carrying out all this times, because I'm more interested just in the theory that arrives at the things, so that then when I'm looking at truly classical things, then that makes sense, and it has like a setting in the wider world of all the things. So he talks for a while about models such as plates, shells, or rods, or the motion of liquids and films, or shallow channels, composite constructions, the setups, the viscoelastic, the deformability, the compressible and incompressible fluids, rigid connections, rotating connections, degrees of freedom, degrees of mechanical freedom, applications of machines mechanically, the electrodynamic, the electrostatic and electromagnetic, chemical. In the next page or so, he gets into like a good breakdown of all these different kinds of energy. Talks about the integral relationships and the Lagrangian density and the Galilean transformation. The Galilean transformation is basically the most usual kind of like, it's linear. It's just like a translation in coordinates from one space to another, most usually. It talks about structure and microstructure, and the Cosserat continuum, Cosserat, Cosserat continuum, that was considered here quite a long time ago, and I'm going to be studying it some more. But it seems that it's just kind of like a system of springs or a system of levers, or it's a system of arbitrarily small instead of points machines. But that's quite a thing. The tensor of internal turns, the Ricci tensor for the system of enhedrals of the Cosserat continuum. In this case, these enhedrals, what all are as part of a matrix, a grid, a continuum of a lattice-like array things. He's talking about the so that's among the media, say. It's like it's all the same everywhere of this particular variety. Unexact solutions for interacting gravitational electromagnetic fields, tensor representation of spinor fields. Then he oh great. So in this next section he gets into the basic variational principle and then a thermodynamic approach, which has kind of got these really principled accounts of the things. And so one of them is, as I've read about this far and looking at the formulas about Newtonian mechanics, for example, and an analysis of an individual physical object or the energy of physical objects, the process of defining energy for observers, both for the system and its parts. So the observers, besides like a measurement apparatus, which is essentially it's so connected by having a sense, is yet the actual only the participants. So we may ask, what is energy? First of all, we must say that energy is the main model characteristic of physical objects, matter and fields. That can be taken either as a basic primary characteristic, similar to mass in terms of which one can express other physical characteristics, or as a characteristic that can be expressed in terms of other characteristics taken as primary. So this is about the theory, and that energy is great and fungible, and we have, after mass energy equivalency, a way to look at everything as energy, but at the same time, it's really, according to the medium and the actual what's primary in those, what is of those. So this book helps to carefully detail that there are these vital considerations to otherwise keep what's like a popular sort of physics saying, well, everything's just energy, or everything's particles, or everything's waves, or everything forces, or everything's fields, is incomplete. So that's something good to be said for this Sedov's account. This is from about 1984, I say. Of particular importance are characteristics like the totals and its parts for individual objects for an infinitely small time, or if the meaning of an individualized object permits it, over finite time intervals. And it's a very informed and very thorough, a very correct, a very full, and a didactic and a direct education in this book to arrive at, from like basically the contents of a science degree or a mathematics or physics degree into this approach, and that is well something that has these fundamentals of the principles that would be considered classical or modern classical, and as they're very much thoroughly ubiquitous in all applications today, these days. Talks about the internal energy, the free energy, and the entropy. That being about this thermal second law. about the Euclidean and pseudo-Euclidean and Riemannian and pseudo-Riemannian space for general relativity, whereas I have that just all like it's Euclidean and then it's as with regards to like displacement a little bit instead of like an arbitrary geometry, but that's for another time, I suppose. About the geometrical interpretation of all the things. Newtonian mechanics. Now, perhaps I've read past where he has a couple different things, and one is the explanation for the thermodynamics first law, the variations in their interrelationship in the co-moving and the observer's reference frame. That I'm just going to scan back briefly and see if I find what was that particular list of things here. Here it is. These laws for individualized small volumes, dV cubed, of particles and fields take the following form. 1.17 is the first law of thermodynamics, the conservation of energy. And 1.18 is the second law of thermodynamics, the entropy increases, or time irreversibility. And then 1.19 is the equation of continuity. So this is energy and entelechy, and so it's least action and least gradient in our theory of sum of histories, sum of potentials. So these are the laws of thermodynamics and the laws for particles and fields. For the total energy, the virtual energy, the corresponding elementary virtual works for external body and surface forces, total virtual external influx, and the external influx, and an additional virtual flux, arising from the fact that arguments of U and S contain various electromagnetic quantities or quantities expressible in terms of derivations of the laws of motion and similar characteristics of matter and fields. So that's something I really found as profound, because it's like, this is why we have two laws of thermodynamics, and that's because it's a very kinetic course. Then the other thing I wanted to mention was he's got a great little summary of types of energy according to this introduction. So if I didn't misplace that, then I'll find that here. Perhaps it was in the introduction. Yet what I'd hoped to find was it. Because it talks about different kinds of energy, like mechanical energy, electrodynamic energy, and otherwise it's helping to show that when we talk about a theory and it's like its energy is conserved, it's energy according to these kinds of energy in their media that all live together in one field, all of these superimposed fields about these space frames and frame spaces that move in it, that move in the media. So I'll find that briefly here before closing this book for a while. And I'm just kind of reading this as I've been reading Richardson's electron theory and Tinkham's quantum mechanics, and then this a little bit. And this is quite a modern work, and it's quite well regarded. Here the quantum effects manifest themselves through separately defined thermodynamic notions and through functional relationships introduced by quantum mechanics. So that this sort of work is very well at rise of all the premier theories. Here's the section on energy. If we wish to fix the types of energy, their dependence on the main parameters, and the laws governing their transformations into each other, we must rely on the data concerning these types. We will start with nuclear energy. This type manifests itself in strong and weak interactions with elementary particles, strong nuclear force. Next type is electromagnetic energy. This is the main characteristic of electromagnetic fields. Third type, chemical energy, has an electromagnetic nature. It is associated with the energy conserved in fuels and explosives, the energy absorbed or liberated in chemical reactions in both inorganic and organic chemistry and the like. It is clear that this type of energy is closely linked to the mechanical phenomena occurred in chemical processes. So this helps to affect it. That's a matter of dynamics is chemistry. And so what energy gets liberated, or what energy in states of in changes of states of matter, or exothermic and endothermic reactions, help to affect that. This kind of energy is kind of like the dynamic energy, because all otherwise something that's an object of chemicals like H2O or caffeine or some other chemical or something like that is just according to its state. And so it's by this nuclear energy, electromagnetic energy, kinetic and thermal energy. So, but its chemical energy is of course related to like any kind of its active sites with reflect to anything that make for the dynamics of reaction, that then the energy is released, or as energy is converted into other forms. So chemical energy by itself has its own category here in Sedov's system, yet is its own thing. Mechanical energy. Primarily, this is the potential and the kinetic energy of relative motion related to the work of acting forces and moments of various order. So here there's kind of a study of that in moment and motion. The main ones being of gravitational and electromagnetic nature. This we call electromotive force and gravitational force. But then also any kind of matters of equal, opposite, and or motion, rest, and equal opposite, and moving and unmoving, and worlds turn in the bit. The internal potential energy of continuous media also belongs to this type. So that's just to give this, like, he's saying it's a mechanical reduction if whatever else is going to be part of the system, whether it's vacuum physics or direct positronic C or however else it's still going to be, it's kinetic in a sense. It's inertial, it's kinetic. In Newtonian mechanics, we can consider the work and the respective energy associated with inertial forces. So he says the fifth type is thermal energy, and so this is usually considered as kinematic and kinetic. It's kind of like at a molecular level, how much motion is arrived at via heat energy, thermal energy. And finally, we turn to gravitational energy. And so this is associated, and notice kind of like this is the last from the nuclear energy, the gravitational energy, but in a theory of fall gravity, they might be the same thing. But one is from the outside universe, and one is like in the center of each nucleus. So that helps to establish that the idea that this gravitational is totally a weak force and the nuclear force is totally a strong force, just on either side of these things, or that like the thermal and the mechanical are two different things, was they kind of have the same thing. And then the electrical is of these various kinds of ways, when it's electromotive or electromagnetic or otherwise is for matters of current and voltage. That potential difference and is often called electromotive force because it's how much voltage will turn a wheel, but it's not necessarily the same thing. These are interfaces where they come together. That this is the kind of thing. So that's what I wanted to read from Sedov today, is this great sort of organization of an explanation that there is the empirical and it's relevant. And so we have our theoretical, and then this wider theoretical makes for that there's the virtual work and the variational principle after usually just thermal first law, conservation energy, or symmetry, that makes the Lagrangian account these kinds of symmetry. And so that's considered very, very solid, and always so, especially in any kind of classical formulation of things. And as it gets right up and directly into the adiabatic and non-adiabatic for the variational principles, and for discontinuities, it says, when this rocket takes off, there's a strong discontinuity for a brief zero time. How do we solve that the hypercube distance equals 1? It remains to be seen. These are the kinds of things. So then there's another several hundred pages in this book about the ferromagnetic, magnetizable and polarizable media, moments of dispersion, of finite volumes and liquid ellipsoids, Kasner-Minkowski, Maxwell, Einstein, Kinnersley. He mentions Kinnersley several times. Kinnersley, Kinnersley. The Riemann, Kinnersley and Chitre, Chitre, Hauser and Ernst. About neutrino fields. He's got a lot going on with neutrino fields because these are arbitrarily small points and particles again, but they're really theoretical particles to a lot of people. But in Sedov's world, they're a usual thing. He talks about the author of in the presence of external electromagnetic fields, this effect is imposed on the effect discovered by the author of successive transmutation of the discontinuities in the gravitational and electromagnetic fields. With regards to Sibgatulin's, Sibgatullin, Sibgatulin's neutrino fields in general relativity. And then he ends with some appendices explaining representation theory with regards to group theory and hypercomplex types of numbers and or spinners or spinors or spinners. Great little book. To the reader, we would be grateful for your comments on the content, translation, and design of this book. We'd also be pleased to receive any other suggestions you may wish to make. And they give an address. This though would have been in 1984 or so. Another little book here that was started to be read a while ago, and it's about the pseudo differential. This is Charles Nash on the differential topology and quantum field theory. And what I'll be looking to do is read through this, and he talks about like self-duality and anti-self-duality. It's like when our variational principle has a variational principle. Yang-Mills, and Yang-Mills is to be figured out as just kind of like after Kaluza-Klein, then we got Yang-Mills, and it's a way to do a dimensional analysis about the local gauge. To obtain an elliptic problem, we have to choose a local gauge. There's a gauge condition with regards to metric connections. To find this gauge connection, we have to look To find this gauge condition, we have to look at connections in the neighborhood of A. Consider a small perturbation of A in a gauge direction that is subject A to an infinitesimal gauge transformation G by writing G equals e to the TF, approximately on the order of I plus TF for T small. So the A sub G equals G inverse AG, it's after like the Hermitian or the adjoint, plus G negative 1 DG, that would be the differential. So on the order of the identity minus TF A, identity plus TF, plus I minus TF D, I plus TF. So it's got this X plus Y, X minus Y bit. It's kind of, that was one of the other things that kind of came up in the descriptive differential dynamics, is like X squared minus 1. How about, X to the million minus 1? It's X to the million over 2 plus minus 1. A plus TD AF in this variational setting, where it's like it's variational, yes, it's reciprocating. Taking the derivative shows the tangent is just the derivative times the function. However, this is a tangent in a gauge direction. Kind of reminds of director cosines. That's another thing that's to be learned pretty carefully is director cosines for the spherical geometry, and spherical trigonometry, because then it's used a lot in the formulations, and people who would have come up with these formulations initially, that would have been their bread and butter, that these ones were better, but then that's because those ones got cumbersome. But when it comes to taking them back down and apart, it's like, well, yeah, they have their own way. So director cosines are something important. We can decompose the tangent space. So about the tangent space, normals and subnormals, tangents and subtangents, the director cosines. This makes it clear. The non-gauge directions are given by kernel, dA, orthogonal complement to imaginary part of dA. So it's all quite in a complex setting. And that's one thing that's tough to figure out when it's like everything has thoroughly been complexified for all these matters of keeping it simple in the spherical, when we're just adding up amplitudes like these parts of it. and because it reduced writing a formula from like a half a page block of a matrix and all its different things to like a term. The problem being that's that has kind of lost the rest of the representation. This analysis suggests a natural gauge condition to impose on perturbations of A to a Dirac connection A, big A plus little a, namely the condition d star A equals 0. So making a case for symmetry is like it's got to arrive at this. This is its condition. And so this is just an example of an algebraic and geometric and symbolic derivation here for the instantons and monopoles section. As with regards to something that is with regards to connections and conditions in the gauge of the theory, how to arrive basically at things just like in geometry is like the hypergeometric, 0, 1, and infinity, with that being like a point and infinity or just a straight vertical line at all, and otherwise the field of finite values. These are the kinds of things that the author is getting in here into about the pseudo differential. Here in this quantum field theory, mentions holonomy, Holonomy, the holonomic and holodromic are both examples of how to gather these things together to make for a singularity theory that yet has analytical character, kind of like non-real functions that yet have analytical character. This is for these kinds of things: the holonomy and the holonomic, holodromic, monodromic, the cohomological interpretation. Attias Singer, Weizenbach, about the Laplacian. Following Attia, Hitchin, and Singer, we now make these two assumptions. So yeah, and up to the Chern character of things, Chern classes, Pontryagin. This is kind of this course about Donaldson after Attia, Hitchin, and Singer, assuring that M sub k exists as a global Hausdorff manifold. C.F. Bernard, Christ, Guth, and Weinberg. About the instanton, it needs to be irreducible. About irreducible representations, because otherwise it's they're multi-valued, and so then that involves a multiplicity theory account more than the inductive account. So this derivation is just trying to put together an inductive account and the conditions under which it will hold true without missing any. Whereas Sedov's account is more like this is everything is sufficiently general, and then within that are these kinds of considerations. Bogomoni, these all being names, Euclid, these all being names of the people whose derivations just like, do you remember formula 8.116? It's like, no, it's like Bogomoni. Oh yeah, Bogomoni, right. And this is reckonable as the component form of the Bogomoni equation, F equals negative star d sub big A phi. So is it mass times acceleration? It's like, well, here it's negative star d sub A phi. Thus, instantons which are invariant under time translation are monopoles. Of course, we are using the term instanton in a loose sense, since time-independent instantons necessarily have infinite action, which we usually exclude. And it gets talking about time translation invariance. The elliptic geometry of strings. Schwartz and Witten, De Hoeker and Fong, and Green, Polyakov, Bose. So this is just kind of part and parcel of the physics that then gets into these kinds of approaches and accounts. Then this other book here is something that's to be picked up and read some more. So it's about the path integral, and the idea that Swanson's path integral has that we approached it and got into that is pretty much about the classical parts, and it's working up the line integral. And then with regards to these things, then this other stuff gets figured out. So with regards to notions of Fediev, of Dirac, Yamamoto and Tanaka, Rivers, Martin, Clowder. These people haven't written papers on path integrals. Zumino, Glauber, Martin and Schwinger, Weigel, Richard Feynman is always showing up. J.D. Jackson, Classical Electrodynamics. Someone recently recommended that book to me, J.D. Jackson's Classical Electrodynamics, but here we're reading O.W. Richardson's Electron Theory of Matter, from which it would have been derived and built, and also the nuclear theory and so on. Grassmann. So Grassmann's after Clifford and comes up with octonions and Grassmann algebras, which are kind of like algebras, but they just have more combinations up above that all fall back down. So the more complex algebras are not necessarily about complex numbers, just about the more foldings, as they were, that can arrive at these things. Well, that'll about take us to the hour, but these are the books I want to get to that, and then continuing to read from the Fourier style analysis in case Gonzalez Velasco may have still so much more to say about the history and the derivation of the Fourier style analysis, which makes it so that we can arrive at honestly and conscientiously any kinds of differences at all to make for these modern Fourier style analysis, and also looking for what goes in the derivations for the unlinear parts, then where they live and how these things are, because they do exist, and then otherwise if we don't really know where or how they live or how they are, then there's this whole terrible matter of that the theory is inconsistent and incomplete, so it cannot be verified or certified. It might be accurate, but that's not science. And so then I guess that is science, but it's not a conscientious, open-minded, wide-eyed science. It's just an inductive account, and as we kind of arrived at from the beginning of this talk, it's like that does not suffice. We have a fuller dialectic to make it so that each of us can have each our own philosophy, psychology, and science, and theory, and as well, I'll be pointing at the same one called true. Hey, have a great day, gentle readers, fellow earthlings. Happy holidays.